Right, I'll get started on the next section now. So the morning session will be on non-linear. So there's a few workshops that we'll do. So what I'll do, I'll go through the presentation, and then the first workshop I will run through that, so then you're a bit more comfortable when you're doing it. And then we'll give you a bit of time to do that first workshop, and then I will introduce the second workshop. And then possibly do part of it, so then it's easier for you to follow. Okay, so we'll talk about non-linearities and what the different sorts of non-linearities are. So the thing to bear in mind here is that the non-linear training is actually 2 days of training. So I'm sort of compressing a lot of that content into a very short space of time. So the material is available on the customer portal, and with some of the workshops, there's the, if you like, the theory chapter for that particular workshop. Okay, so when we have our stiffness matrix, so basically when we're solving our model, we're solving Kx equals F. So for a linear model, this stiffness matrix doesn't change. So when you have a nonlinear model, any change in contact status, so you'll have an area in contact that may change, that's going to change your load path and your stiffness of your structure. So you need to account for that change in a nonlinear model. So that the impact of that will change the stiffness matrix. So the second thing that has an effect on the stiffness matrix is the change in shape of your structure, or the changes in shapes of the elements. So they may rotate slightly, they may elongate slightly. So when that happens, their individual contribution to the overall stiffness matrix will have a cumulative effect. So it will change the stiffness. So if you take a simple structure like a flat sheet, so initially that doesn't have any out of plane stiffness. So as soon as you apply a load out of plane, the structure will deflect out of plane. And in order to take account of that deformed stiffness shape, you need to update your stiffness matrix based on the change in position of the nodes. So with a linear model, that isn't taken into account. And that's why we say that for linear models, we assume small deflections. So the deflections don't have an effect on the stiffness matrix. So the last one is a change in material property, or Young's modulus of the material. So when your material goes into yield, it will have a different effective Young's modulus. So it will no longer be linear in that range. Okay, so also in line with this is the amount of strain. So normally for most metals, when you get to yield, the strain is quite small, so it's only a fraction of a percent. But materials like rubbers can undergo quite high strains, so sometimes of the order of 2 or even 300%, and that deformation can be recovered. So it's not only when you have permanent deformation that it's considered a material nonlinearity, it's also when you have strains that are quite large. So usually when you get up to, say, 5% or above, you generally need to calculate your strain differently. And that is only taken into account when you turn on nonlinear effects. Your strain is calculated as a log strain. Okay, so in terms of sort of visualising this, or sort of instead of us just talking about one single value, so here we've got a stiffness matrix here on the left-hand side, and this is our structure. So these individual stiffness terms come from the initial positions of the nodes. So as the nodes move and rotate, so usually if an element rotates by more than 1 or 2 degrees, then these stiffness terms are no longer accurately representing the stiffness structure of of the geometry. So if you like, each one of these terms you can think of as the effective stiffness at each node. So some of these will be shared because there'll be shared elements at some of the nodes. Okay, so this, even if you don't have any metal plasticity or any contact nonlinearities, which you won't have in this model because it's a single part, so you purely update the stiffness matrix based on the change in shape of your structure. Okay, so with contact nonlinearity, so here we've got two parts that are in contact. So mathematically, the contact is enforced with springs. So as you get more and more nodes coming into contact, you add more of these springs. So that's going to add individual terms, or it's going to modify some of these terms in the stiffness matrix. So as you get a change in status of your contact, that's going to change your stiffness matrix. So in our linear models, where we have linear contacts, so bonded or no separation contacts, we don't have any change in status of contact. So we don't need to track that contact status change, and we don't need to update the stiffness matrix. But in a nonlinear model, when we account for contact status change, you have to account for this change in contact status. And you generally need to do this in steps or incrementally. You can't arrive at a contact status in one hit. It has to be iterated towards. Okay, so with changing material properties, so at the bottom we've got an elastic slope. So let me change to a pen. Okay, so in this region here, the material will behave elastically. So you apply twice as much force, you get twice as much stress. But when you start getting into the plastic range, so over this range from 3 to 4, there will be an effective or an equivalent Young's modulus. So we generally refer to this as the tangent modulus. So depending on the behaviour in this plastic zone of the material, so we can have different ways of describing that material property. So it usually comes down to where your material data comes from. So as an absolute minimum, you would have just a one slope that describes your nonlinear behaviour. Okay, so even though that's in effect a linear slope, it's still considered a nonlinear behaviour, because there could be parts of your material that are still elastic, or parts of your structure, sorry, that are still elastic, and other parts that are in the plastic zone. Okay, so when we're solving a nonlinear model, so the way the solver works is slightly different to a linear model. So this black line, we don't know ahead of time. So this red line here is basically our initial guess at the stiffness matrix of the structure. So as you apply or try to apply a load based off that stiffness, you'll have a certain displacement. That displacement is applied to the structure, and then you get some internally generated forces. So if they don't balance, that means that our stiffness matrix at this point of displacement is too different to what we initially guessed. So we then calculate a new stiffness matrix based off the new conditions. So if it's contact, geometry or material property, and then we try to apply the load again. So we keep repeating that process until the difference between the internally generated forces versus the externally applied loads are almost in balance. So you'll never get this difference between the externally applied load, the internally applied load to be zero, because of the way computers do their calculations. So effectively each one of these red slopes is a new stiffness matrix, and we refer to it as an equilibrium iteration. So with nonlinear models, you're typically solving multiple equilibrium iterations, and each one of those is equivalent to a static linear solution. Okay, so here this illustration just demonstrates the process. So you can sort of read through this afterwards, but basically we try to apply a load. We get FA is what we're trying to apply. F1 is our internally generated load, and then the difference between FA and F1 we refer to as our residual force imbalance. Okay, so ideally we want this to be very close to zero. Okay, so the solver won't repeat this process indefinitely. It has a reasonable cap on the number of times it does or attempts to apply the load. So if it can't achieve what we call convergence, it will try and apply a smaller fraction of the load. So when you're solving nonlinear problems, the idea is to break this dotted curve, which we don't know ahead of time, into small piecewise linear segments. So that way you have to do less of these equilibrium iterations over that small segment. Okay, so it's a balancing act between the amount of load segments you break your total load into versus the number of equilibrium iterations per sub-step, as we call it. So a load, when it's broken down, we break it down into sub-steps. Okay, so here this just illustrates just really a force balance. So on one side we've got our residual forces, and the other side we've got our applied loads. So this difference between these two, we try to balance that to within a small difference. Okay, so if we look at the non-linearity of contact, so there's basically 5 different types of contact behaviour that you can have. So bonded and no separation, these are basically linear contacts. Okay, so the frictionless, rough and frictional are what we refer to as non-linear contacts. So they're non-linear because the status can change. So when I say status, the amount of area in contact, so you could go from parts being in contact to being separated, so losing contact. So that means that your load part will no longer be through that contact. So contact is probably one of the more challenging non-linearities to deal with, but there are parameters you can change within a contact that help achieve convergence. Okay, so if we look at a very simple example, so here we've got a lug and we're pulling up on this pin, and there's a contact between the pin and the hole. So by default that's defined as a bonded contact. So depending on the sort of interaction we want, so if this was welded all the way around there, then a bonded contact would be appropriate because it's not going to want to try and separate. So in order for it to do that, it has to break the weld, but that's probably going to be unlikely. Okay, so here you can see that the bottom of this lug follows the pin. So I've exaggerated the deformation here, so you can see the sort of pinching that's going on here. So with the bonded, the parts can't slide relative to each other, nor can they separate. So with the no separation, you can have a small amount of sliding relative between the contact. So if that sliding is quite large, so when I say small sliding, it's usually a fraction of an element length. If it's more than that, then it means that your contact is more than likely non-linear, and a no separation contact is inappropriate, and it's most likely going to be giving you incorrect results because you've assumed small deflection, but the parts have slid a lot relative to each other. Okay, so with a frictionless contact, so you can see there's a large, it's an exaggerated large gap opening up underneath. So as soon as there's a negative contact pressure, the parts will separate from one another. Okay, so and along the sort of side here, there's going to be sliding going on with no resistance to sliding. Okay, so a frictional contact. So here we've got quite a high friction coefficient. So if you look at the sort of the red contour, so you can see that the red band is a little bit bigger here. So at the top where there's a lot of contact pressure, there's some sticking going on because we're not overcoming the frictional resistance right at the top. But sort of towards the sides where the normal pressure, sort of normal to the that roller there, is low, then there's some sliding taking place. Okay, so as opposed to the frictionless case. So with a rough contact, so you can see the red band is wider. So let me change to a pen. So if we sort of draw a V where there's sort of sticking going on, that V becomes narrower. Okay, so with the frictionless case, so it'll be even narrower again. So a rough contact you can think of as an infinite friction coefficient. So you can't have any sliding motion going on, but if you get a negative contact pressure or a tensile pressure across your contact interface, the parts will come away from each other. So you'll get a gap starting to form. Okay, so when we're post-processing a contact, so we have a contact status. So this tells us what state the parts are in. So it could be sticking, sliding, or it could be in what we call near or close contact, or it could be far away from being in contact. So the status in combination with the contact pressure. So the contact pressure tells us how hard the surfaces are being pressed together. So if you have a bonded contact and you look at the contact pressure, if there's a large area of negative contact pressure and it's not welded or glued together, then it's likely that those parts are trying to separate, but you're not allowing them to separate because you've got a bonded contact. So you can basically rerun the model by changing or splitting the area up so that only the positive pressures are in contact. But normally if you do it that way, although you're running a linear model, you're able to do that multiple times until you iterate towards a solution where you've only got positive contact pressures. So it's much easier just to switch to a non-linear contact and let the contact take care of that for you, putting just the positive contact pressures into contact. Okay, so in terms of the statuses, so sticking, so there's no relative movement either in the sliding or the normal direction. So a sliding contact, so this can happen with a no separation contact or with a frictionless or a frictional contact. So it can't happen in a rough contact because we can't have sliding. So a near contact is contact that has a gap, but it's inside what we call the pinball region. So the pinball region for contact is a way of describing, it's almost like a search distance that searches for impending contact that could be about to happen. Or for a bonded contact, if you have gaps, it will be, if it's inside the pinball, it will ignore that gap. So it will transfer load even though there's a physical gap. Okay, so a far contact is anything that's outside the pinball region. So it's not touching and the gap is bigger than our pinball. Okay, so here we've got the contact statuses for bonded, so you can see it's all sticking. For no separation, in this case, it's all sliding. For a frictionless, we've got a sliding and a near, so there's no sticking going on there. So with friction, with the friction coefficient, there's a small band across the top here that is sticking. Then across the side, it's sliding, so that's still touching, but the normal pressure isn't enough to prevent the sliding because we've overcome the frictional resistance. And then with the rough contact, basically anywhere where it's touching, it will also be sticking. So anywhere where it's sort of, there's no sort of sliding in here, it transitions immediately to a near contact, which is within the pinball region. Okay, so if we look at a bonded contact, so this is a contour plot of the contact pressure. So you can see that there's quite a large amount of negative contact pressure. So somewhere between this sort of colour here, that's where it's sticking. So it's sort of trying to pull away on the outside, and there's a sort of a band that's sort of sticking in the middle. So because we're over constraining this interaction, if these parts were truly free to move away from each other, then switching to a non-linear contact isn't going to produce the same results. Okay, so if we reduce the area in contact to exclude the areas of negative contact pressure, it's still going to keep that middle band bonded together. So it might take a few iterations of changing the faces that are in contact until we get a meaningful result. So although we're sort of linearising the problem, we're doing it multiple times. So it's much cheaper to do this as a non-linear contact. Okay, so it's the same sort of thing with a no separation contact. We've got large negative contact pressures, so that's not letting the contact to separate. Okay, so with a frictionless contact, so you'll notice there's a large area of basically a zero pressure. There's no negative pressures. So anywhere where it's zero, it's basically it's opened up and there's a gap, and then the contact force basically redistributes and goes through the top half of the pin. Okay, so you can see that there's a pressure distribution where it's a peak on the outside, then it falls away to a minimum on the inside, then it goes back to a peak on the outside. Okay, so this is a more realistic representation of what would be happening if the parts weren't welded together. Okay, so with a frictional contact, so in the middle here, that's where it's sort of trying to pinch together, and it's even possibly starting to separate, so, or it's a very low contact pressure. So you'd have to look at the contact status in combination with the contact pressure to figure out what was actually going on there. And you can see the same thing. We've got a zero contact pressure on the bottom part of the pin. Okay, so with a rough contact, so we see a similar sort of effect, but the angle of wrap, if you like, is much greater because we've got that sort of sliding, sticking going on there. Okay, so under real conditions, we'll have a friction coefficient of somewhere between 0 and 1. So you can input friction coefficients that are higher than 1 to sort of simulate sort of not totally rough contact, but sort of closer to sort of an infinite friction coefficient. So in most cases you can look up in handbooks what typical friction coefficients are for say steel versus copper or steel and steel, and then just input that into your contact definition. Okay, so with material nonlinearity, so we'll focus more on metal plasticity because that's more it's encountered more often. So sometimes we want to predict if a part undergoes plastic deformation, what shape it will return to after you remove the load. Or it could be that you've just got some local plasticity happening on a model, and it doesn't really affect the overall shape of the structure. Okay, and then in some cases we use this to our advantage. So if we're doing metal forming, so often we'll need to take metal plasticity into well, not only into account, but we use it to form our final shape. Or if it's in some sort of structure that absorbs energy from a crash, we use it as an energy absorbing mechanism. So you need to have the material property defined in order for that to take effect. Okay, so the material properties for metal plasticity. So often you can get very basic data. Sometimes you can get a tensile test result or tensile test data. So tensile test data is normally given in engineering stress, engineering strain. So up until a point where the specimen necks, we can have conversions for engineering stress to true stress and engineering strain to true strain. So when we input material properties into the software, ANSYS automatically understands that the material properties are true stress, true strain. So you have to convert them. Okay, so in terms of the way we describe the stress strain curve, so we can have just a linear relationship. So this is called bilinear because there's the elastic slope and the plastic slope. Or we can also do a multilinear. So here we basically have pairs of plastic strain versus true stress pairs, and that will give us a curve shape. Okay, so if you've got digitized tensile test data, you can convert it to this multilinear curve. So it generally depends on what it is you're interested in. So if the behaviour in the plastic region is of interest, then a multilinear will more accurately represent the behaviour than a bilinear. So with a bilinear, if all you've got is the strain at break and the ultimate stress, you don't know what happens between the yield stress and the ultimate stress. So you generally represent it with a bilinear material. So sometimes all you will have is the yield stress. So for most metals, usually a good approximation is to have your slope to be somewhere between 5 and 10 times the yield stress. Okay, so there's also two types of, or two different ways of specifying what happens after you have yielding happening. So there's what's described as a kinematic hardening. So basically when you yield, so you go into the yield region and then you unload. So when you unload along an elastic slope. So if you apply stress in the reverse direction, you'll have a new yield stress in the compression direction. So the difference between those two yield stresses for kinematic hardening is 2 times the original yield stress. So if you load quite high up into the plastic zone, when you're unloading you can actually start yielding while you're still in a tensile stress state. So because this difference between these two yield stresses is 2 times our initial yield, then it can sometimes result in an unrealistic behaviour. Okay, so this is mathematically possible, but in general it's not physically possible. So you generally don't use this for extremely large strain cyclic loading. So when you're loading, unloading and then reloading, it's generally not an appropriate material property to use. Okay, so the more often used one is this isotropic hardening. So this circle here, if you like, basically describes a stress state where yielding occurs. So we're basically looking along a 1, 1, 1 vector where 1, 1, 1 is along these three principal stress axes. So as you yield, the material will strain harden. So that's basically this slope here. So this is basically our effective tangent modulus. So then when you unload, the new yield stress in compression is 2 times whatever the yield stress was when you started unloading. So this results in a more mathematically stable behaviour, and you won't get unrealistic yielding while you're unloading if you've loaded to quite a high stress. Okay, so if we look now at an example of how we take commercially available material data and convert it to for use in a non-linear simulation. So normally you get a range of yield stresses, and then you'll get tensile and ultimate, and then the percentage elongation or the engineering strain when failure has occurred. Okay, so this is an example of basically stainless steel sheet, and then different material grades and the different properties that we've got. Okay, so using those conversion equations I had before, so here we've got, so the 240 and 270 are basically our sort of double yield point. So we just decide which one of these we take as our yield stress. So if we look at the engineering strain, so the proof stress is basically when your strain is 0.2%, and that's basically what we find here. So if you convert the engineering strain to true strain at very, very low strain values, then you can see there's virtually no difference. Okay, so when we go up to higher values, so at yield, for example, so 530 is our engineering stress, but our true stress is a lot higher, it's 742. So our engineering strain and true strain differ quite significantly. So there's an elastic strain component in there, and the remainder is basically our plastic strain component. So we generally ignore, or we can correct for the elastic strain component when we're sort of calculating our effective slope. Okay, so if we take the tangent modulus as the change in stress divided by the change in plastic strain, so we get a, so there's a bit of a typo here, I think. So we wind up with an effective tangent modulus. So when we input that into the software, so ignore these numbers here for the moment, this is just for illustration. So you put in your yield stress, so in that case it would have been 240, and then our tangent modulus is our 1485. And then when it draws the two curves, well, it basically draws two slopes. So this is to give you a feel for the relative slope of these two curves. So you obviously want the tangent modulus to be less than the elastic modulus. So one of the common mistakes people make when they're entering this data is that they think they're putting this in megapascals, and they're putting it in pascals. So you wind up with a material that behaves with plastic behaviour right from the outset. So we see a lot of people make the mistake when we're doing the training. So I still make it when I'm putting material properties in if I'm not paying close attention. Okay, so you just need to make sure if it's in pascals, you use a Pascal sort of Pascal units. and then so you can change the units you're entering this in, but if you don't want to, you can just type in the value in the correct units. Okay, so so this is just reiterating that point. So so don't use a zero slope. So a lot of people like to use an elastic perfect plastic material property. So if you've got a yield stress, use something realistic for a tangent modulus, or use a very, very small slope. So it's mathematically unstable if you use a zero slope, because what you're essentially saying is that for any value of strain above yield, you'll have the same stress. So essentially what you're saying there is, for no increase in force, you will be able to increase the strain or increase the deformation, and that's not physically meaningful, at least not for a metal. Okay, so you can, if you want to, use those two data pairs to build a power law relationship, and then from this power law relationship you can build a multilinear stress strain curve. So this is probably a little bit of overkill to do this, but this is just to show that if you had tensile test data, you could do a power law fit to your data, or a linear fit to a log-log plot of your true stress, true strain, to come up with a sort of a better representation of the material properties. Okay, so again, just saying, converting to true stress, true strain for your tensile test data, plot it as log-log, and then just do a least squares fit to sort of filter out the error. Okay, or simplest way is just convert your data points and then just enter them. So if it's digitized data, you don't need to enter every single data point. You just need to have enough data pairs to capture your curve shape. Okay, so here for a multilinear hardening, so I'll show this when I do my example. So you basically put in plastic strain and then yield stress. So it's very important that you put in a zero here. It won't accept anything other than zero when you're filling out this table. So then the curve that it shows, in this case, doesn't show your elastic slope. It just shows your plastic behaviour. So the reason that they show the data in this way, you're basically comparing the subsequent slopes. So these should basically decrease, and they should never go negative. So your last data pair will just continue on with that, whatever that slope was. So if you get strains higher than this, it will basically extrapolate this curve. Okay, so generally it's a good idea to have data that will cover your expected strain and stress range, but where you've got local singularities, you're not going to account for that. So you just have the data in the expected range. Okay, so with multilinear, so it doesn't really add any extra value if you over-specify the properties. So when I say over-specify, that's having too many data pairs. So if your tensile test data has 100 data points, you don't have to have 100 data points to define your table. So it will take you quite a while to enter that, and it's not really going to give you any more accurate results, because it's highly likely that, say, 10 data pairs will give you the same curve shape. Okay, and then the important part here is to check that the tangent modulus is decreasing. Okay, so you can do that very simply in Excel, or just look at the plot that it gives you as you're entering the data pairs. Okay, so if you're creating your own material, or your own non-linear material, it's always best to add that to an existing material. So that will have the base Young's modulus, and then it's a matter of choosing between bilinear or multilinear, and then inputting the curves. Okay, so you've got multiple options available there. Okay, so for rubber materials, so these are always nonlinear. If you define a rubber material model, it won't let you solve unless you turn on large deflection effects. So because the engineering strain approach isn't, not that it's not valid, it will give you very inaccurate results for strain. So rubber materials, you often get way more than say 5 or 10%, which is what you'd see in a metal. You can often get 200 to 300%, and it's fully recoverable, but it has to be calculated using an incremental strain and also a log strain approach. Okay, so I'll do this demonstration model in a minute. So in terms of combinations of all of these nonlinearities, so this is probably about as complicated as you can get. So we have self-contact, or this rubber boot coming into contact with itself. So that's a changing status contact. So the shapes and positions of these elements are changing significantly from the starting point to where they've wound up. And it's highly likely that there's quite significant strain going on within this rubber. So all three of these effects are taken into account when we turn on large deformation effects. So large strain, large displacement, and changing contact status. Okay. All right. Okay, so I'm just restoring the archive. Okay, so going to the engineering data. So I'll just show you that it's a linear elastic material at the moment. Okay, so the behaviour here is set to 2D. So I'm just going to the properties of the geometry. So this is just to make the model solve a lot quicker. Okay, so it's an axisymmetric model, so that means that it's basically an angled disc, and then there's two plates here that are being pushed together. Okay, so if we look at the contacts, so that red line there and that blue line basically represent surfaces of revolution, so they're basically revolved around an axis. So because this spring is going to deflect as it's compressed, it will come into contact, and then when the load is removed, it's free to separate if there's a negative contact pressure. Okay, so on the top there's the same sort of thing. So there's a frictionless contact, and then there's a small edge along the bottom with a no separation contact. So that's just to stop the just to stabilise the model. So even though this is it's basically a revolved cone, it's just to stop it sort of sliding. Okay, so we've basically got a displacement loading. So we're fixing the bottom plate, and we're pushing the top plate down, then we're moving it back up. So let me just switch my units. So we're just compressing it by 5 millimeters and then lifting it back up by 5 millimeters. Okay, so if I solve the model, okay, so if we look at the total deformation and we animate. So the spring basically returns to its starting position. Okay, if we look at the stress, okay, so our stress goes up to nearly 3,000 megapascals. So obviously that's quite unrealistic. Okay, so to make this model more realistic, we need to add nonlinear material properties. Okay, so in order to do that, we basically have to right-click here and then duplicate. And then, because I want to use different material properties, I select the link and then I delete. Okay, so now I'll go into my engineering data. I will add and just double click for multilinear isotropic. Make sure I change my units. Okay, so and I need a temperature, so I'll just use 22, so it will assume that it's constant. So I'm just putting in some values here. Oops. Okay, so I'll just use another value here. Right, so I'm just making these up. They're not exactly the same as the workshop. Okay, so I close that. So the other thing we need to do here, so this is just to get around a bug. So we've got to change the analysis type to, oh, sorry, I've messed that up. Let me delete that to be safe. So that's the other step. You need to delete the geometry and then you just right-click, edit. Okay, let me try that again. Okay, so I'll delete that engineering data. Okay, so let me refresh to bring in those new material properties. Okay, change it to 3D and then okay, and then edit. Okay, so because this was duplicated from my previous simulation, I should be able to just simply rerun it. Okay, so it's still saying axisymmetric, which is what I want. Okay, so I don't need to change the material because that structural steel now has non-linear properties. Okay, but what I need to do is, let's just leave it as default. Okay, so this will now, so sorry, I need to turn on large deflection effects. Okay, so it's on. Okay, so now if I look at my deformation, so you can see that the top plate has now come away and the spring has remained in a deformed state. So if we look at the equivalent stress, okay, so you can see it's 291, so that's basically yielded the entire cross section. So we have plastic strain. So because there's the cross section has basically gone into yield after it's being compressed, and that plastic strain will remain after the load has been removed. Okay, so if I re-compressed that spring, I'd probably get more deformation as I compress the spring a little bit more. Okay, so if we drag and drop the reaction force, okay, so if I create another result, so here I'll use a user-defined result. So I'm just going to use the absolute UY displacement. Okay, so now what I'll do is I'll combine these two into a chart. Okay, so my x-axis I want to be my displacement. So don't want to plot time. So basically force reaction in Y. Okay, so basically that's basically my force deflection curve. So you can see it's unloading and then it's basically coming back to zero before my displacement has gone back to zero. Okay, so it's gone plastic and then unload and then basically no reaction when it's sort of lost the contact. Okay, all right, so that sort of concludes that. Does anyone have any questions on that? No. All right, so I'll bring around, for those of you who don't have access to the portal, I'll bring around the files for the non-linear workshops, and then we'll get started. So we'll sort of go through in order. So if you do the metal plasticity one first, and then the post non-linear buckling has got two stages. You do the linear buckling first, then the non-linear, but I'll sort of get you started with that one. Okay, and then there's the Tormax and the fracture tool.